So we have a pressure vessel, a gas tank. Think about it like that. A hydrogen tank in the back of the truck, something like that. Some dimensions, and we pressurizing it. A very classical problem. You did it in probably formula bodies, the first semester, yeah, first course. Now, two formulas that every, or at least one formula that every mechanical engineer should know, in addition to F equal to ma, in addition to sigma equal to my over a, or MC over I, and C over I, that's what I meant. In addition to that, is the thin wall pressure vessel problems. So you have three components of stress here, principal stresses. One is the hoop around, that's the killer one, PR over T. P is the pressure, R is the radius of the nominal radius of the pressure vessel, and T is the thickness. The other one is the axial one. If the ends are capped, this is also going to have an actual stress, but half the hoop, you can see that PR over 2T. And the stress through the thickness. The stress through the thickness of the wall, what is it? It says 0, but wait a minute, why is it 0? It's not 0. You just look at the inside, it's pressurized. How could it be 0? If you were standing against the inside of the pressure vessel, and the pressure vessel was pressurized, don't you feel it, some force on your belly? Because it's pressurized. That's sigma Z. It's not 0. So why do we say for pressure vessels, or thin wall pressure vessels, sigma is 0? Look right there. That's what we read in the formula bodies. How do you justify that? How do you justify that on an interview, the guy would really say, "Do you understand these?" Yes. Can you tell me why is that 0? Because on the inside you have a pressure. Pressure in the thickness direction is the pressure that you apply, or stress. So what would you say? Is that a fair question to ask on an interview? Okay. The problem is not 0. That pressure, that stress is not 0. It's actually the pressure on the inside. And what is it on the outside? What is that stress on the outside? Sigma Z on the outside. What is it? There it is 0. Inside it is not 0. So you cannot say that the stress is 0 because on the inside it has a value, on the outside it has a 0. So why are we saying that this is 0 then? It has to do with that R over T. Very big. R over T is very big. Thin wall pressure vessel. T is much smaller than R. So the ratio R over T is 100. So you take the pressure multiplied by 100, that's going to be the hoop stress. Multiplied by 50, that's going to be the actual stress. And the pool pressure in the radial direction, the best it can be is P. The other one is 100, the other one is 50. Actually, the radial one, the biggest one that it can have is 100, whatever the pressure. So that's why we assume it is 0. Okay, so we're going to solve this problem. We can do it based on extracting surfaces or making the surface directly by itself. I'm going to do both. What about symmetry? Use as many planes of symmetry as you can. You have seen a problem like this. What was the problem that you saw that kind of resembled this kind of a geometry? Does anybody remember? Which one? Yes, rotating disc. The rotating disc problem. So, if you were convinced there that any sector that we take can be used and it's going to be, patterned around the disc, same thing is here. You can take any sector that you want, 30 degree, 45 degree, 90 degrees. The advantage of taking 90 degrees is that you don't need a new coordinate system. You don't need a new coordinate system. But if you take anything but 90, for example, then you need a coordinate system to apply those symmetry restraints. And I can guarantee you on the test, if I wanted people to do that coordinate system, I will tell you take a 30-degree sector. So don't take 90 then, and you're going to lose more torque. Whatever the components of that particular portion is. Okay? So I will take a 30-degree sector. Okay? And by the way, half the height. Uh, let me see now. I don't want to concentrate on these dimensions. So I'm going to make my own dimensions, okay, so that I don't have to worry about this. All right, so let's go ahead to Catia. Those of you who are watching this tape or recording, I'm ignoring dimension. What? What happened? Okay. Let's start with solid first. Okay, I'm going to start with solid. So on that face, I will sketch. You know what? On purpose, I'm going to create a whole solid and then make a plane and cut it. Make a plane and cut it. Okay? So let's do that. You can say, can I not make that sector to begin with? Yes, you can. But I'm doing it differently. So, well, obviously here I'm going to go to part design because I want to make a solid object out of that. Okay, so let's say this is half of the height, half the height, half the height. Now, I would like to cut this thing, take a 30-degree sector. Okay? So I have to create a plane that is 30-degree rotated, for example, with respect to one of the vertical planes. Here's how I'm going to do that. Look, if you know, great, I have no problem. Plane, but let's see. What is one of these? It says offset, angle. It looks like this. Angle, something with angle. Okay, so it says what is the rotation axis? I'll say Z axis. What is the reference? So for example, 30 from, I don't know what I picked here, YZ plane. And I'm going to put a 30-degree here. So you can see that it actually created a plane at 30 degrees to that. And I'm going to use that for cutting purposes later on. See this? Okay, now get the split. Get the split. Get the split. Let's first cut it with respect to YZ and keep the other side. Let me flip that. It really doesn't matter. And then I'm going to cut it with that inclined plane. Okay, so another split. Read it carefully with respect to that inclined plane and keep the other side. Flip it. Obviously, that was not what I wanted. That's okay, no problem. Double click on it, flip the direction of the arrow, and say, do this thing any way you want. Okay, I just wanted to show you how you create planes with certain orientation. Okay, so this is it. Let's apply material to that. Material, metal. Okay? And we go to generative shape design to extract the faces. Extract the top face and the side face. Oh, notice that it won't do it. I have to do it separately unless I go to this bag. No problem. Do it again. There. And we don't want this. We hide it. We cannot delete it because these surfaces are coming from that object. We cannot delete them. Yeah.
Those surfaces keep the same material that you apply.
Yes, yes. Because once you put it on the part, anything that's in there, no surfaces are in this part. Okay? Of course, look. Part steel is down here. Everything that's here is in that part. And part is taking the steel properties. Yeah. I assume that already I have. I'm sorry, say that again? Half the height. Half the height. You don't want to lose much of that. I already assume that suppose this is half the height of the thing. Okay. Now, because I don't want this issue of connections and things like that, why don't I join them? Join them. Join this to that, so that we don't have that issue of seams and things like that. Now, because later on I want to apply a certain restraint on these two edges, there is no problem because these two edges happen to sit in the YZ plane. On the other guy, the other two edges are not in the YZ or XZ or XY plane. So I have to create a bonus system for that. And let me remind you how we do it. That that thing is right here at the very bottom. There's no way you can miss it. Axis system. When you ask for the coordinate system, automatically it creates it at the global origin, which is down there, right there, and oriented with the global coordinate system. I don't want that. So first of all, it makes it easier for me to see things. For the origin, I'm going to select this top one. Okay. This, oh, actually, that one. Yeah. Let me undo this. You know what? I want to put it on that corner, which is not aligned with the edge that I cut. You can see that. But I have a choice of putting any of these coordinates on direction that I want. For example, if I want x along this line, no problem. I say here, x, put the x there. Rotate it so that x is there. You see, x is along that line. The x of this coordinate system. Okay? You say fine. Let's go and do the rest of the problem. I have a question for you. Would you like me to go to the advanced machine tool or generative structure analysis? Okay, no problem because it's so easy. Click on the surface measure. Select the entire thing, and put a reasonable size there. If not, you can change it. Say okay, and zap it. You like that? Okay. Say okay, and then we exit that particular surface measure module. The rest is the same. So we're going to go to the generative structure analysis. Already we meshed it. If you want to see the mesh, right-click mesh visualization. It's right there. Okay, we can see that. Deactivate it. Okay, now we're going to, let's see now, thickness. Thickness on that face, whatever it is, 0.02, 0.2, whatever. Just remember that these formulas that I wrote down for you are valid for thin wall pressure vessel. So if you want to check against those formulas, this better be small thickness. I mean, in principle, you can make it a million miles, it'll do it for you. It's garbage, basically. So all I'm saying is that we go ahead and recklessly do this thing. But now, okay, so let's go ahead and apply our restraint. So this is user-defined restraint. This edge and that edge lie in the global YZ plane. Global YZ plane. You can see that. Global YZ plane. They do not move in X. Rotations exactly the opposite. Those two other edges lie in this coordinate system conveniently. So let's select the other two edges. I'm going to uncheck these. This edge and that edge lie not in the global, in the user, and I created my user. So the coordinate system that you use is with respect to this coordinate system that you see created. And can you help me with that? What do I fix translation-wise? What do I fix? Z, good, good. Direction 3 and rotation, exactly the opposite. So this and that and okay. Is there something else that I have forgotten to do? The bottom edge, the bottom edge, I cut it, I left it alone. So I have to do that. So the bottom edge, and don't clump it. You clump it, you get color. It's completely wrong. This is not clump. It's a symmetry. With respect to, be careful here, with respect to the global one, for example, it is in the XY plane. You could have used the other one, but I changed it to global. I switched it from user to global. It's in the XY plane, does not move in Z. Rotations is exactly the opposite. Okay? Last thing, pressure, load. I don't know what I have, 100 psi. So we're going to apply pressure. Now, I'm pretty sure that you're going to have to select both of them. I'm pretty sure, in spite of the fact you joined it, you have to put it on this. You see this? That's suction, of course. You put a minus there, right? That pushes it in. Okay. Minus. You're going to have to do this thing separately. So on the other one, and that's correct. You can see that's outward. Okay, always pray. These are not too bad, but they're safe. I'm not going to even save it. I'm going to run it. Done. Look at the transformation. That doesn't surprise you. Doesn't surprise you, because the piece of this entire structure that's most flexible is on the top and the bottom. Trying to expand the periphery is going to be harder. Okay, but these two bulge out. Okay, if you look at the one Mises stress, you're gonna do some detailed work here. It tells you that in this particular problem, the biggest stress is around the seam up there, and I agree. If it fails, in all likelihood, it's going to be at those wells. But do not take these numbers for granted, because the critical area, one critical area is on the top, I understand, but to get good stress distribution with shell elements on that top is not going to be possible. Okay? It gives you a rough idea, but it's not possible. Generally speaking, when you do this kind of a thing, unless you're designing these guys for the well and things like that, you're interested mostly in the hoop stress and things like that. Okay? So be careful of taking these for granted. Now let me show you something. If I want the stresses here, by the way, look, as I go down here, they're all the same color. If you put the cursor on it, actually, the numbers are also all the same. You see this? Let me zoom in for you. They're all the same, all the same. As you get closer and closer to the top, things will change. But in that area, in that vicinity, everything is blue. Everything is essentially the PR over T and PR over 2T dumped into the formula for one Mises stress. But if you plot the principal stresses, it will actually give you PR over T and PR over 2T. Because principal stresses, one of them is the hoop, the other one is the axial, third one is zero. Third one is zero to it. So if you go and plot the principal stresses, which was totally useless for beams, here you can actually get things that you did with Dr. Green and whoever taught you in the first course. Principal stresses, and in fact, these values are PR over T and PR over 2T. In fact, if you zoomed in closely, you see one of them is double the other one. Yeah, see that? The hoop stress is double the other one. You multiply 5 by 2, you get 10. Okay. Now, one other thing I want to show you. You might say, you know what, this is fine. Let me actually put this thing back where it was. Average ISO right there. Nothing exciting. Now, which stress is this? Principal stress. But if you want to know which one you're plotting right now, let me go there. Under more, you can say which one you want, C11 or C22. If I change this thing, it's going to be half the values. But my point is something else. Sometimes you get the von Mises stress, for example, or any of these, and you want to stay away from that top because you know that that top could be garbage. You want to stay away from that. Only you want to show the stuff, for example, here. So what you do is you go and create, let me deactivate this block first of all. No, okay, we can leave it. You go and create group. Catia calls it group, and there are different ways of making it. For example, I can make I don't know, a box group. It says, okay, where do you want this box to be placed? Well, I don't want it to be placed there. So I'm going to move it. I can move this. Let me see, does it cover that? If not, I resize it so that it actually covers it. Sure, yeah, okay. There. Just show me the stuff in that box. No problem. Let me hide the box first of all for you. You go to the place where you decide on what you want. You say, just show me the box group. Don't show me any other garbage. Don't show me any other garbage. Just show me this. Wait a minute, what's all these colors? Why are the colors different? Are they not supposed to be the same? Yes? Strings? No, strings are there. This is just looking at this particular piece. Just looking at that zone. Yes? What is the range? What are the numbers? They're all the same. But for plotting purposes, it has to do something. Just be careful. Colors don't mean ignore the numbers. Those numbers are all the same. Okay, listen, I am not going to do this thing the third way. Let me just show you. Let me just show you. I'm not going to finish the problem, but I want to show you how to create this geometry in 20 seconds. Let's start with the part. Okay, 20 seconds. It's not going to take more than 20 seconds. I can guarantee you that. On that plane, I will sketch an L. Exit and revolve it. Catia does not call this thing shaft. In generative shape design, it calls it revolve. See, these are different ways of making surfaces. See that? These are different ways of making surfaces. We have already done extrude, and there's one here which says revolve. So it says revolve this about the z-axis. By how many degrees do you want? Let's say 30 degrees. You don't have to join these. Just like when I extruded, I got a single surface. You just revolve it. The rest of the problem is exactly the same. So let me stop this recording first of all, and then I talk about